Okay, I hope that you had a good long weekend. Everyone seems to be back. And what we were doing last time was we had started with the review of mechanics of materials. And if you remember, I started by introducing the two main categories of loading, mechanical versus environmental. And we talked about static and dynamic loading. And the focus here, basically for this review, is the mechanical loading. And I think this is where we stopped last time. Let me consider different types of loading, mechanical loading. So let's look at A and B, tension, compression. This is hopefully is clear. And then we talked about torsion and shear. And if you remember, I told you that torsion and shear, they have some similarities. For example, if you think about the cross section of this rope or this cable here, if you think when you are applying torsion in the cross section here, you're actually shearing. And when you are having shear, whether it is simple shear or as in this example, a double shear, you are also shearing. And the force is parallel to the cross section, as you can see. So they are they have the same nature. And at the end, we talked about bending. So when you bend a piece of anything, may I borrow your notebook? If you bend any kind of plate, for example here, steel plate, then what you have, for example in this configuration, you have tension on the top and compression at the bottom. This would be the opposite if I do this. So what you have in the cross section is actually a combination of tension and compression. So, thank you. Although they look very different from tension and compression, as you see up there, you see that bending and tension and compression, they have the same nature. So just like torsion and shear, they have similar nature. Bending and tension compression, they have some similarities. Any question about this so far? Now, we need to develop some tools and ways to calculate a stress, a strain, and basically the things that you have seen in mechanics of materials. So we'll start doing that right now. Let's first start with tension or compression, normal force. Here on the left-hand side, we have shear on the right-hand side. Let's first focus on normal force. If you want to calculate the stress, I hope you remember from mechanics of materials that you have to divide the force, in this case by the area that the force is being applied to. And since we have, let's say here, tensile, it can be also compressive stress would be very similar. Maybe it's two. Let's use a different pen. The compressive stress would be also similar. You divide force by the area that is perpendicular to the force. And the units are important. So the units, depending on which unit system we work on, it can be pound per square inch, or you have heard PSI, or Newton per square meter, which is called Pascal, exactly. Of course, there is KSI, which is 1000 psi. There is kilopascal, megapascal, etc. Why do I call this engineering stress? Does anyone remember from mechanics of materials? Don't scare me, you remember. Why is it engineering stress? Why just not a stress? Because we are dividing the force by the original area. So this word original here is key to make this an engineering stress. If we wanted to define a stress, we would just divide the force here by the area. What is the difference? Because, for example, when you apply tension, the area gradually becomes smaller. So as you apply more force at every instant of time, this area is not equal to what it was originally. So you may also define a stress as the force divided by the area as you're applying the stress, and this area becomes smaller in case of tensile stress, or larger in terms of in case of compressional stress. You may remember this figure. If you apply tension or compression, the area actually is going to change. So that's why we call it engineering stress. Now, how about shear stress? Shear stress, tau, is defined the same way. If we are talking about engineering stress, you divide the force divided by area. But pay attention which force we are dividing. We are dividing the force which is parallel to this area. So in terms of normal stress, you are dividing the force which is perpendicular. Shear stress is parallel. So we may want to note that this is like normal stress, and here we have shear stress. How about the units? The same. A stress is a stress, has the same unit. Force divided by area. Questions so far? Well, what are some of the examples of these kinds of stress? For example, simple uniaxial tension. You can think about the force that we have in cables. The cables here, all they are doing is pulling the deck of the bridge. Right? Look at these cables here. If I take one of these cables and I cut it, all I would see is a tensile force. It's pulling the deck. You agree? So if you were to calculate the stress, you would just divide this force by the area. In mechanics, typically if we have tension, we use positive stresses and strains. This is the opposite, for example, in soil mechanics. Compression is positive. But in mechanics, and in this class, we use positive stresses for tension and negative for compression. Just a convention, nothing to worry about. How about compression? In this very same bridge, if you look at the piers, or in general, if you look at any two bodies, if they are sitting on top of each other, what you see at the interface, you have compression. So compression is In this case, let's say uniaxial. We are looking at this bridge here. Now, if you look at one of those piers, if you simplify it, all you have is compression. If I cut any of these columns and I draw the free body diagram, which you are familiar with from other classes, what you see is basically a force which is compressive. And in this class, we use negative for compression. As I said, if you are taking soil mechanics, everything there is in compression. So it's kind of useless to make everything negative. So people said, okay, let's have positive for compression. But here we have tension positive, compression negative. Now, these are simple. You may also have those very uniaxial. Uniaxial, you have in a cable, the tension was just in one direction, the direction of the length of the cable. In terms of the piers or the columns, compression is only along the length of the column. There are situations where we have multi-axial stresses. Examples, one, let's look at this pressurized vessel. If you look at the membrane, the container, if you cut a piece of this container, and if the thickness is small, what you have, if the thickness is much smaller than the other dimensions, what you have is a two-axial or biaxial stress condition. Is it easy to see from here? This doesn't work. There is no projector for this one. If you are inside a soil, inside the ground, or in this case, if you think about a fish in a tank or in river or ocean, what you have is a three-dimensional triaxial stress condition, meaning that if you are inside the soil, if you take a cube inside the ground, you have pressure coming from the top, but also the material around you are pressuring you in all three directions. It's the same if you are inside, let's say, water. If the liquid inside this tank has a triaxial stress condition. These concepts should be familiar to you, but any questions? Is there anything unclear here? Okay. Those are all normal stresses. Shear stress. For whatever reason, shear is always a little bit more difficult for some people to imagine, but you always have to think about some sort of having a glue. If you have glue between two surfaces and you are pulling them apart, what is the glue experiencing? It's shear. In our applications, for example, one good example is when you have pinned plates. So you have here 3 plates are pinned together with this pin. Now, on the right-hand side, what you see is the free body diagram for that pin. So the plates, they try to pull this pin. The pin is experiencing pressure, but if you look at any of these horizontal planes here, what you have is shear. So you are shearing the pin at this cross section. So here is the pin, you're shearing it like this. And why? Because to counteract these compressive forces, you need to have shear force applied. And you may have seen, or you may see in other classes, that in the other context, if you consider, for example, the wind pressure, This is more like an environmental load in a sense. Or if you think about earthquake, what you are experiencing, what the structure is experiencing is shear, base shear. Now that the different types of stresses and forces are clear, we move to deformation. So if you have a rod, original length is L0. If you pull it with the force P, the original cross section is A. If you pull it, the stress, the engineering stress, would be force over original area, A0. Stress at any time would be force over the area. And what would be the strain? You've seen the definition in mechanics of materials before. Change of length over the original length. So a strain is a unitless quantity. It's the relative change in length. So you see, if you go from L0 to L0 plus delta L, the change in length is delta L. This is in tension. So as you see, we said stress, if it is tensile, we use positive numbers. And you see that the bar is elongated. So automatically, the strain is also positive. We get back to that in more detail, but you probably remember from mechanics of materials that if the material is linear elastic, and we'll talk about this a little bit more, what it means exactly. The stress and the strain are proportional. And the proportionality coefficient, let's say, is this elastic modulus, which has different names like Young's modulus, elastic modulus, stiffness, so on. This is only good if the material is linear elastic. And we'll get back to that. What does that mean? Now, this is for tension. Try to see if you can write similar things for compression. So put the force P, original area is A0. Let me use another color to make sure. So I use P and original area is A0. Try to write a stress, change of length, then a strain, see if it's positive, negative. Just do it right now. So the original length is L0. See what happens then. Yes. Are you talking about this one?
Yeah, shouldn't it just be Ln minus LL? Why are you adding plus Ln?
So the new length is L0 plus delta L. And the original length is L0. So change of length would be the new length minus the original length. This is for tension. So first it was L0. That's the original length. And then it became L0 plus delta L when you pull it. So the change would be what we have now?
First term is L0.
Yes. It looks like LA.
It looks like LN.
I'm sorry. Yes. Please keep me in check with the handwriting over this. I'm getting better, but yes. So it is L0. So for the compression, let me see that. I typically have to see 3 correct answers before writing things down. I've seen one. That would be helpful. Just so to make sure you remember mechanics of materials, there is no other. Okay, I've seen 3. I know it's simple, but it's good to write things down. So our stress will be again P over, let's say, engineering stress is A0. If you just write a stress, is over A. And normally we write it with a negative sign. So we use a negative number for this, or we just add a negative. So it will be negative. That's just a convention. Compression is not negative in nature. It's just that we want to be able to differentiate tension and compression. A strain here will be, I'll try to write this nicely this time. If you compress something, the length will shrink. Right, so it will be the new length will be smaller than the previous one, let's say by amount delta L. And this is the original length. So now I use parentheses to make sure that things are clear. And then you divide this by the original length. And simple simplification gives you this. And when the stress we use negative, the strain also becomes negative, so smaller. And when you plot the stress-strain in this relationship, if you have linear elastic material, the modulus will be still a stress over a strain. But I leave it there because we are going to talk about material properties in a lot more detail. Okay, so yes, question? So I think I mentioned this to you before, but again, I like to emphasize that when you have normal stress, whether you have tension or compression, you induce volume change. In some of the homework problems, we actually calculate the volume change, but let's just have it there. How about the strain due to shear stress? So now we know how to calculate the strain in normal stress in one direction. How about shear stress? Shear strain. Shear turns out to be a little bit more, a little bit less intuitive, I would say, the way it is defined. So the shear stress is the shear force divided by the area. But the shear strain is defined as the relative change of angle. Remember, shearing is all about distortion. There will be no volume change. So all which is happening is this cube is not a cube anymore. It becomes a little bit distorted. And to measure that, yeah, there is a little bit of, so this is supposed to be gamma. That's a typical letter that we use to show shear strain. So gamma is expressed in terms of the shearing displacement in the direction of the force over this length, L0. So you want to see how much rotation in a way you have. So you divide delta L over L0. You may think about this as, so this is gamma. So all the little C, so shear stress is just the force over the area. In this case, the force and area are parallel. Shear strain is this deformation over the length. You can think about it as somewhat if you consider this an angle, it looks a lot like tangent, right? What you are calculating, it looks a lot like the tangent of theta. And since the deformations are very small, the tangent and the angle, they are kind of equal. They are very similar if you write the angle in radian. If this is not familiar to you, don't worry about it. It's just important that you realize shearing is about distortion and how it is being calculated. One thing which is very important in terms of the concept is that shearing doesn't cause volume change. So normal force, volume change, shear force, no. Distortion. Now we go to talk a little bit about material properties. This is a materials class, so basically we want to talk a little bit more about the relationship between a stress and a strain, which is defined by materials properties. I assume that everyone is familiar with linear elastic materials. What is the definition of an elastic material? If you want to explain an elastic material to someone else, let's say your sibling who is in high school, or someone who is a freshman or a sophomore, how do you explain it? What makes it?
An object which can retain its shape after being
Retain its shape after it is deformed. It's a good definition. Any other way of expressing this? Does anyone have any other? This is a good one.
When we deform the shape, it will go back to the original.
Exactly. This is another way to express the same thing is that it bounces back to where it was. It retains its shape. That's elasticity. If a material is elastic, if you want to show it on a graph like that, the stress strain, normally we say, okay, if you load it and unload it, it follows the same curve. That's why you see these arrows here. This is mathematically explaining or graphically explaining just what your friend said. It goes back to where it was. How about linear? What does linear mean? Again, if you want to explain to a sophomore. The name shows, right? When we say linear material, it means, yes.
In a line.
Exactly. A stress and strain follows, the relationship is linear. There is a line. It looks not trivial. I'll show you some examples that you will see that sometimes it's easy to forget this simple explanation. So when we say linear elastic, we are actually talking about two properties. One is that the stress strain is linear, a line. Second is that it goes back. If you put an arrow upward, there is an arrow downward. And it is very easy to represent this just with elastic modulus. You use elastic modulus to show the linear relationship between the stress and the strain, as you can see here. A linear elastic material is not defined by one parameter. You actually have to have at least two. So you have to use either E and G, which is the shear modulus. We get back to that. Or you have to use E and Poisson's ratio that you have seen before, but I'll review that for you in a second. So you need two parameters. To describe a linear elastic material. You need two. Now these two should be two independent parameters. It could be elastic and shear moduli. It could be elastic modulus and Poisson's ratio. Just for, I forgot to mention the units for elastic modulus. The unit is just like the units of stress. Why? Because a strain doesn't have a unit. So if the stress is in PSI or Pascal or kilopascal, then elastic modulus will have similar units. To give you an idea how the elastic modulus is for different types of materials, there is this little graph here. So on the top, you see different categories of materials. We have metals, we have polymers, composites, and ceramics. And you kind of can compare how the stiffness is compared between different classes of materials. Looking at this diagram, what can we say? We can say that typically metals have higher stiffness than polymers, even higher stiffness than most ceramics. Is that correct? So it is kind of useful to have some sort of an idea of where each material is. For example, if you look at steel and concrete, which are two important materials, you see that steel is one order of magnitude stiffer. So these kinds of graphs are useful to give us a general idea where we stand with different materials. Now, the question is why? So if we go back to the diagram that I just showed you, and we look at the metals, and here is diamond, which is the highest, and then you have metals and concrete and other materials. So far you have just seen them. In this class, we want to also learn a little bit about why. Why do we have different stiffness for steel and concrete? It turns out that if you had a way at the Elizabeth to go and look at how two atoms are bonded with each other, we actually can measure that today. If you look at this is interatomic force versus interatomic separation. If you measure how the force between two atoms inside a material changes with the separation between the two atoms, if you try to move the two atoms and measure how much force there is between them, the slope here at equilibrium gives you an indication of a stiffness. It turns out that the stiffness that we measure for different materials has a lot to do with their interatomic bonding and interatomic motor. We'll get back to this later on in the second module, but it is important from now to kind of develop this multi-scale view about the materials, not just looking at the numbers. So this is very interesting. And we said that we need at least two parameters to describe linear elastic materials. Not one. And the second one could be Poisson's ratio, which looks very strange in my slides right now. The definition of Poisson's ratio you've seen also most likely before is if you are stretching material in one direction, in the other direction it's going to contract. So if you divide the strain in one direction to the strain in the other direction, the ratio is defined as Poisson's ratio. So here you are looking at lateral strain versus, let's say, axial strain. And you notice a negative sign here. This is used so that you don't get negative numbers. Because if you stretch something, it's going to contract in the other direction. So the ratio will be negative. To make it positive, you have to add a negative sign. If you compress it, it will expand in the other direction. Again, negative. To make it positive, we add a negative sign. And we can also compare the Poisson's ratio between different groups of materials. Concrete, ceramics, between 0.2, 0.25, metals, 0.3, polymers, 0.4. What does it mean if the Poisson's ratio is larger? It means that if you are stretching the material in one direction, it is affected a lot in the other dimension. That's what it means. How about the units? There is no unit because you are dividing a strain over a strain, so there will be no unit. I explained here is a little cartoon which shows that if you are pressing axially, you are actually getting lateral expansion. Basically what I told you, why we have a negative sign and the range of numbers for different materials that you can see here. So, we could use elastic modulus and Poisson's ratio, but we can also use, let's say, elastic modulus and shear modulus. If we plot the shear stress versus shear strain, whether you do a torsional test or you just have a simple shear or double shear, and if the material is linear elastic, so this is only for linear elastic material, then you also have a linear relationship between shear stress and shear strain. And the proportionality coefficient is shear modulus. Typically we use it for that. And in terms of units, it's again the same units of like a stress. So in terms of units, you have PSI or Pascal, etc. So this is shear modulus. So remember that you need two parameters. You can choose to use E and Poisson's ratio or E and G. Another parameter which may be not as familiar to you is the bulk modulus. In soil mechanics, this is a beloved parameter, modulus, and this is very simple too. So in previous cases, we were looking at change in length versus change in the stress, let's say. Here we are looking at the relationship between pressure and relative change in volume. So if you have especially a triaxial stress state, like it's very common in soil mechanics, very common. You have pressure coming from all sides. Change of volume to the original volume, this will be your bulk strain in a way, and here you have pressure. And the proportionality coefficient is the bulk modulus K that you can see here defined. Since we are using, we are not going to use this as much. I've just included this for the sake of completeness. The relationship, there are some useful relationships between these different parameters. So for example, you may be familiar with the relationship between G and E. And you see that the relationship is a function of Poisson's ratio. So that's why you can either use elastic modulus and Poisson's ratio or E and G. And I'm also giving you here the relationship between bulk modulus and Young's modulus. So you can see this relationship too. And this is Poisson's ratio. Now, from one-dimensional case, we want to move a little bit towards other types of loading. So here, if we have only one-dimensional stress, you can calculate the strain in both directions. It's not very difficult to do that. When we have, in a more general case, when we have three-dimensional stress condition like we have here, we have to use the so-called generalized Hooke's law. Wherever you think there is need for me to explain more, please let me know. I don't know how much you remember from the strength of materials. I may make assumptions which are not very accurate, so please feel free if something is not clear. So how does that work if we have more than one stress? If we have, let's say, a triaxial in the most general case. So if you want to calculate the strain will be a combination of, or a summation of, a strain, uniaxial strain situation. So since everything is linear elastic, you can say, okay, this triaxial case is equal to one axial, then we have only a stress in x direction plus y direction and z direction. And how does it work? Well, if you have a stress in the x direction, a strain will be just a stress over E. This is linear elastic material. Very important. In the other two directions, we talked about it. The strain in the other two directions, which will be y and z, would be just negative Poisson's ratio times epsilon x. That's by definition. We can write this for all these three directions similarly. So we say, okay, if we have a stress in one direction, we know how to get a strain, and the other two directions will be related the strain to the strain which was calculated through Poisson's ratio. This negative is not very clear when I look from the back. So here there is a negative sign here. So now, for example, if I wanted to write epsilon x for the triaxial case, it would be this epsilon x plus this, right? You have to see wherever we have epsilon x, we have to sum it up. So it would be a summation of epsilon x from the first one plus epsilon x in the second one and epsilon x in the third one. This is called superposition. It's only possible if we have a linear elastic material. So let me write it down. Superposition. The linearity of the material allows us to use superposition to say, okay, this stress state is equal to a superposition of this plus that plus that. Now, if I want to know how much is epsilon x, I say, okay, it is the epsilon x from the first block plus the epsilon x from the second block, which is negative Poisson's ratio times the stress in the second block plus the epsilon x in the third block. So if you compare this to that, this is the Hooke's law in uniaxial case, something you are all very familiar with. This is Hooke's law, the generalized Hooke's law for, let's say, triaxial or biaxial stress field. Yes? Now, before I let you go, try to write epsilon y and epsilon z for yourself. Try to see you can do it. Like, that would tell me that you got the basic idea of the generalized Hooke's law. Now, if I want to write epsilon y, I also have to sum up the epsilon y from the first block plus the epsilon y the second and third. Because remember, the real stress situation is a summation of the sources. So this one would be so the one which has the same direction has no Poisson's ratio, of course, and then from the other directions you get the strain through Poisson's ratio. Okay, I'll bring the handouts for those of you who didn't have it. apologize for that.